We're live. Hi. Hi, everyone. I'm James. Friends call me Jim. You can all call me Jim. This is Johan. Hi, Johan.
Hi, James.
Yes.
Sorry, I was calling you Jim before.
No, okay. No, you can call me Jim. You're not my friend, right?
Not yet.
Yeah. So this is these are my coordinates over here. Developer advocate with Pivotal, and Johan is a I'm not sure. What do you do?
I will talk about that in 4 slides from now. So I work with a
You had your chance, man.
No, yeah.
Okay, so anyway, I've written several books. Johan actually had something to do with some of those. I work for Pivotal. Pivotal is a company that helps the world transform how they build software. We curate Spring, Pivotal Cloud Foundry, which is a cloud platform that runs on top of all the major cloud platforms, as well as on-premise. So it's this consistent cloud platform that you can use. Pivotal Labs, we engage with customers and help them with agile processes. And then the new kid on the block is Pivotal Container Service. For some reason, the acronym is PKS. I guess it's because it's production-grade Kubernetes. And we have some principles and practices. There are 5 of them. 3 of them are right here. My favorite one is over on the right, and that is be kind. It's refreshing to work for a company whose one of their prime directives is to be kind. I think I'm a pretty kind person, unlike Johan, so I don't really need a company to tell me to be kind. But it's very refreshing, and it's especially in today's environment. For God's sakes, let's be kind to each other. Let's treat each other like we want to be treated.
So the Pivotal definition of be kind is slightly different from my definition of be kind, but go on.
Okay, I'll go on.
One more commercial.
Also, we're going to have a spring party in San Francisco, Spring 1 in December. Come across the pond and come party with us.
Okay, over to the more serious stuff now. Can you go 4 slides back?
Why don't you just do your own slides then, if you're going to be...
This is on a Mac. It's not on a Linux system. So these are the books that James wrote. I started with one book, Pro Java X8. I took that over. The publisher wanted better quality. The others, are still on my to-do list, but it's, there's much work to do. So apart from correcting James' books, I work for Gluon. I've been working with Java since it started. I was doing my PhD at Delft University of Technology, and there was a new language, new programming language, and I needed a programming language to do some computations. And that, by the way, have nothing to do with quantum computing. So Jim thinks I know something about it, but because I have a PhD in physics. But I try to explain that physics is a broad area. But to Jim, physics is just going to the gym and lifting weights, and so that's all the same. So I had a Spark station, and I wanted Linux on that Spark station.
Is this going to be a history lesson, or this extended biography? Or are you going to get to a point? Do you have a point?
Do you want to talk about quantum computing?
Sure, yeah.
Okay, in a minute.
Okay.
So there was, I had a Spark station. I wanted Linux on it. There was no Java on Linux, so with a bunch of people, we ported Java to Linux, and that's how I got started with Java. I've always been involved in end-to-end Java, combining the world of the small with the world of the big. And today, that means combining the world of mobile devices with the world of cloud devices. So that's what we do with Gluon. So we bring Java to mobile. So today it is possible to run Java applications on mobile and couple them.
You actually ported Java to Linux. I think you...
Did I forget to mention that?
You forgot to mention that.
Okay, so...
Right. That was pretty cool stuff.
If you rewind 1 minute, you will...
I saw it in the slides, but you just didn't mention it.
Okay, so Java on Linux. I think I mentioned. Didn't I mention it?
You said you needed it on Linux, but you never said you ported it.
Okay, we need to keep you awake for 3 more hours.
Okay.
So so Java is important on mobile, and Java works on cloud systems, and Java is end-to-end. No, you might ask what's the relevance for this in quantum computing. Well, there wasn't until 2 days ago, but we will come back to that later. I will tell you about it because I didn't tell you before.
Nice, thank you.
Oh yeah, so this is what we're doing with Java on mobile. So you have Java, you create iOS app, Android apps, and you connect them via Glue on Cloud Link, our bridge to the enterprise world, to existing and new backends. And you can also use serverless platforms and so. So that's all for the commercial break now. James, at this moment, is still James, will now talk about what we will be talking about.
Okay, great. All right, so this is kind of a roadmap. By the way, I have Catherine Beaumont to thank. I didn't have a roadmap in my slides, but now, because of her excellent presentation on neural networks, she put a roadmap in different places in the slide so we can tell where we're at. And so now, because of that, you'll be able to tell where we're at in the presentation. Where we're at right now is introduction to quantum computing, but we're going to get into things like qubits. We're going to get into axioms of quantum mechanics. I think Johan will be doing a lot of the physical stuff for that. We're going to talk about quantum computing algorithms, quantum entanglement, things you've heard of, more algorithms, and we've got just some appendices in the back that I'll point you to more resources.
Supplementary resources, that means coffee, tea?
Coffee, tea,
okay,
yeah, sure.
Yeah, I got you.
Right.
So maybe one question before you go on boring the people. Okay. Who here has a PhD in physics?
You're just bragging now, right?
Okay. No. Who is here because they think we will stop early and then it will be an overflow room for Venkat? Okay. We're safe, I think.
Okay, good.
Go on.
All right. So who knows what this is? What is that? That spherical thing? Who knows?
There's someone
Maurice, you know what it is, right? It's a what? It's a Bloch sphere.
There was someone who...
Oh, good. It's a Bloch sphere. And so you can represent what's called a qubit with a Bloch sphere. And so it's just off of Wikipedia here, we put that in there. It's just this 3D, this spherical representation of all the quantum states for one qubit. And so we're going to talk about what a qubit is and those kinds of things, but we're going to go into a little bit of history first.
Wait, before,
yes.
you said that I wasn't allowed to do history, and now you start talking about history.
Yes, but it's relevant to the talk, not your personal history.
Well, my personal history is relevant because otherwise I wouldn't be here.
Right, okay.
If there are questions, and we do hope that there will be questions, ask them, but when can they ask questions?
When we ask, we'll say, does anybody have any questions? And then you can ask questions.
Yeah, so something like that.
Yeah,
because
every once in a while we'll do that.
For us, it's to be honest, it's pretty hard to give a presentation on quantum computing.
When everybody keeps interrupting you all the time?
That's the easy part.
But you?
We are developers in front of a developer audience talking about it's a bit out of the comfort zone. It's not clear if we're going too fast or too slow. Then let us know. But how?
So your questions will help us.
Yes.
So back to history. Back in 1940s, none of us were probably around in the 1940s, but I hear that the computers were very large. They took up rooms, and not only were they very large, but they had a very limited memory. Bits, things that represented bits, were actually iron rings, sewed together with coils and things like that. So you had a small amount of memory, and everything was new. Everything was being invented. Software was new to run these things. And so history is repeating itself now. We've got quantum computers that companies like IBM and Google and Rigetti and others are building, and they are in these, some of them require dilution refrigerators to get them down to millikelvins, to get them really cold so that they can be superconductive and display quantum mechanical properties. And qubits, it's the analog, the quantum analog to bits, to classical bits. Qubits, these computers that they're making maybe consist of 5 qubits or 8 or 17. I think Google is working on one that has 49, but but who knows, how long that's going to take. And so we're kind of repeating ourselves. But one important point here, and we've got it on the bottom here, is that quantum computers make direct use of quantum mechanical phenomenon, like superpositions, the ability to be 1 or 0 or a combination of those, as well as quantum entanglement. And so the idea behind quantum computing is to leverage those properties to do things that would be difficult to do classically.
Yeah, so one minor correction, that's not at the bottom. At the bottom, it's our tweet handles.
Yes, and so yeah, please tweet us.
But then in general, the idea is that classical computing started with low power, low memory, high volume, and it became, after a very short time, relatively, our cell phones have much more computing power than the big houses that hosted classical computers. Many people expect that quantum computing will have a similar path. So at this moment, it is not only theory. There are some quantum computers in practice already, but they're not suited for production yet by end users. So here are some pictures of quantum computers, or at least parts of quantum computers. They use very low temperature. They use laser technologies in order to generate the quantum effects. So it is at this moment not yet ready for prime time. But once it's ready, you will have to hurry, because and that is the difference, I think, with classical computing, with Moore's law, which predicts that the computing power or the number of transistors on a chip will double every 18 months. I think that is the law. That will not be the case, in my opinion, with quantum computing. It will go much faster, because in classical computing, if you go from 8 bits till 9 bits, you don't win a lot. But in quantum computing, if you can go from 8 qubits to 9 qubits, you double your capacity, and we will explain why later. But it might go much, much faster. So once a critical barrier is crossed, it can go very, very fast. And it might become scary, because there are many applications of quantum computing that are interesting but also scary. And some. Were you going to do this slide?
No, you changed the slide on your laptop, so
yeah?
I thought you wanted me to change
no,
it on my laptop.
I just wanted to know what the next slide was going to
okay.
be, but I think we discussed that you were going to present the next slide,
Yeah, I would
and
like
I was
to.
interrupting you.
Okay,
then.
no, you're fine.
No, I will interrupt you when you present this slide.
Okay, that's fine.
Yeah.
So why use a quantum computer? So we have in the universe, we have solutions to problems. So as you know, some problems are you have the ability to solve them on classical computers. We do that every day. We're all classical programmers. There's also a set of problems that are feasible on quantum computers that you can't do classically. I think of, for example, factoring large numbers, like with RSA. One of the appeals to quantum computing is this ability to factor very, very large numbers quickly, and you just really can't do that with classical computers, but you can with quantum computers. And so those things aren't feasible on classical, and then there's an intersection between the two where there's some things that you could do on classical computers.
And this is where I have to interrupt you.
Okay, please.
Because there's a misconception often about quantum computing. So it's not that your daily computing algorithms will all need to be replaced with quantum computing algorithms. That's definitely not the case. At least that's not how we envision it now. Quantum computing has different areas where it will outperform classical computing, and in other areas it's simply not suited. So there will be a combination between classical computing and quantum computing in the future. So it's not that it's quantum computing is not simply classical computing, but much more powerful. It's something different, and there are algorithms which we will show near the end where you need both classical computing and quantum computing.
That's a very good point. And so some companies are advocating this architecture where you have this classical computing architecture, but then you might have a QPU, a quantum processing unit, to where you might say, okay, now do something hard, do some very hard problem like the factoring or whatever, and you ship that to a QPU. And so there's a good hybrid kind of scenario. That's a very good point.
Hybrid,
Johan.
yeah, that's a good word. Were you giving me a compliment?
Yeah, I actually was. Do you take compliments
Does
well?
someone take notes about the compliments? Okay.
Yes, and so one of the things that's driving this is that you mentioned Moore's law, right? And so every 18 months, it used to be anyway, that the size
transistors get smaller,
and you can put the same number in half the space or whatever.
Yeah.
But then you can't get much smaller now, right?
There's a physical limit, because if transistors, they are at this moment already extremely small. And so a transistor, which is the core of classical computers, it basically will allow current, or it will stop the electrical flow. But if you make them even smaller, then because of a quantum effect called quantum tunneling, the electrons will still be possible to cross the barrier. So they will be, even though the transistor says stop, there's a possibility that electrons might end up at the other side of the transistor. So in that case, the transistor, of course, stops working, because you assume it will stop, but it won't stop. So there's a real physical, technical limit to the size of transistors. We can't make them much smaller anymore. And therefore, the idea of one of the basic ideas of quantum computing is, if those quantum effects are limiting us from making faster computers, why don't we use them in our advantage? So instead of seeing those quantum effects as a problem, we try to see them as a solution, as a way of new ideas, and actually it's as a way of better ideas, because our world is not composed of zeros and ones. Our world is composed of quantum mechanical effects on different scales. So and our computers are not really representing the real physical world because of the zeros and ones. Quantum effects are the real representation of the real world, and we can turn that into advantages.
So one of the advantages you can turn that into is, as I mentioned, factoring very, very large numbers, 400-digit numbers, 500-digit numbers. I mean, we can't do that yet with quantum computers, but the algorithms are there. So once we scale up the number of qubits that we can have in a quantum computer, we can start doing this. So RSA encryption is based upon being able to factor large numbers into prime numbers. And so Dr. Peter Shor here, created in 1994 what he called Shor's algorithm, and that's this idea of being able to then factor very large numbers. And so he was interviewed in 2013, and he said, if you start factoring 10-digit numbers, then it's going to start getting scary, because we're going to start getting close to that. There's a paper, by the way. This presentation is full of links that you can leverage, and a couple of housekeeping things I should have said instead of insulting Johan so much. A couple of housekeeping things. Number one is I tweeted a link to these slides, and they've got a lot of resources on them. And then the other thing is that we'll be taking a break at about 90 minutes in, something 80 minutes in.
Yeah.
And so, and then we'll take a 20-minute break, and then we'll continue.
That's in 61 minutes from now.
Is that Peter Shor or is that James Gosling? I can never tell. So then,
wait. Can you go one slide back?
Yeah,
because
go ahead.
because you said so. The idea of RSA encryption is to factor large numbers into primes. Well, the idea is actually the opposite, so making sure that you can't factor that. But so one of the so in these slides we want to show the practical reasons why quantum computing might be great, and one of the things, so this Shor algorithm will will make it possible to factor very large numbers. So 4096-bit numbers, factor them in primes, is something that quantum computing can do extremely fast. Now think about the consequences. It actually means that RSA encryption becomes useless, because if it's easy to break the key and to find to decrypt messages that have been encrypted with RSA encryption, then RSA encryption becomes useless. So that's a very important consequence of quantum computing. Now, this will also there are also new ways to encrypt data thanks to quantum computing. So it's not that we will have to live without encryption. The maybe more philosophical, strategical, political problem is that if half of the world is still using RSA encryption and the other half of the world is using quantum computing to break those keys, then the first half is in trouble. Now, it doesn't even take half of the world. If there's just one company, one nation, a few people that can break the existing RSA keys, then they have a huge advantage. So therefore, the race to quantum supremacy is really a very hot race. And there are many big companies and governments that are working on quantum computing, not just because they like the physical effects, but because of the practical consequences of this. So is there anyone in the audience here who is working on a secret project for a government? And anyone in the audience working on a very secret project for a big company who wants to steal or break encryption? Yeah, okay, so that's what I assumed. So that is actually the proof. No one, if you are the first one who can break RSA, will you tell anyone? Of course not, because you first want to break all the keys and then you will tell. So no one here said that, yes, we want to do this. So I think, Jim, they can all do it already.
Okay, gotcha. Great. So another algorithm is Grover's algorithm. And so that's the idea of being able to find a record in unstructured data very quickly. And so that's, it was developed by Dr. Love Grover in 1990. There's a related paper in 1997. I think that he actually came up with this in 95. But one thing that he said was that it's particularly interesting to program a quantum computer because there are multiple things happening in the hardware simultaneously. So you need to be able to think like a theoretical physicist, like my colleague here, and a computer scientist, like us. And so you kind of need to do both of those kinds of things. And so there's a good paper. This link is a good paper. Another thing, go ahead. I keep giving you, letting you not interrupt me. Go ahead.
Another thing is applicability of quantum computing is simulating nature. So as I was already saying, our nature is composed of quantum effects. And if we want to understand this better, what is better to simulate nature by something that resembles nature, especially the world of the very small subatomic particles. So if we want to understand things about quantum mechanics, the best thing to do that is to use the quantum mechanics in a computing unit themselves, so that we can use them to predict what will happen and to explain what happens and why it will happen. So quantum computing will allow us to have a better understanding of the different aspects of quantum mechanics, and it will also allow us to better validate the theories and validate if those theories match with the experiments and with the reality around us. So where it would take classical computers billions of years, or let's say close to impossible, to simulate some processes, quantum computers can do it extremely much faster because they don't have to simulate, they just act because they are those small particles that we want to investigate.
So I thought this quote by Dr. Feynman is very succinct. You know, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanically. and it doesn't look so easy. And he said that in 1981. He was right. It's not easy. The companies are having a hard time creating quantum computers, but it's a cool problem, and it's a cool field for sure. And some of you who watches Big Bang Theory, right? So you probably recognize Sheldon over there, and there was at least one episode where he was playing his bongo drums, and that was kind of an homage to Dr. Feynman, who played the bongos.
What does by golly mean?
I'm sorry?
By golly, what does it mean? And by golly, it's a wonderful problem.
It just means really.
Okay.
It's really a wonderful problem.
Okay, thank you.
Yeah. Oh, hey, not a problem. And so, why don't you take this one?
Yeah. So this is just another example. There's the Open Fermium project. Who heard about it already? So that's an initiative. I think Google.
Google's involved in it.
Yeah.
Yes.
For determining, finding more information about the electronic structure of the subatomic particles. And there are a number of initiatives now that are mimicking the laws of the very small particles and trying to leverage quantum computing for this, trying to find algorithms that will give answers to the questions on what particles, for example, are stable and how will different particles react when they interact with each other. So there are open initiatives about this. There are also closed initiatives about it. But it's clear that mimicking nature is one of the big applications for quantum computing. One of the big, but not the only one. We really have to stress that quantum computing helps finding quantum theories, but it's not only about solving quantum mechanical problems.
So I think you mentioned this, but over on the left is a Nature article on the idea of modeling chemical reactions, and which is it's very useful in the areas of making drugs or solving environmental problems, because then you can model, like you said, using. No,
I didn't say that. I actually forgot it, so it's good that you interrupted me.
I was trying to make you look good in front of the audience. Okay.
So, but that's really important as well. So, in lots of research that involves lots of data computations for finding medical solutions, and so their quantum computing will definitely help. So, one of the goals is that with quantum computing in not that many years from now, every disease can be investigated much deeper. That's actually what you said.
Oh,
so I repeated it.
Yeah, so another thing that they're doing, this is in China, there's a couple of ArXiv papers about this. So the top one talks about ground-to-satellite quantum teleportation, and that's something that we're going to talk about in a little bit. But quantum teleportation is this idea where you can take the state of a qubit and you can like entangle two subatomic particles, a photon or whatever. You can entangle their states, and you can. What they did was they shot a photon, one of the photons there, to a satellite that was entangled with one on the ground, and they would measure the one on the ground, and then measure the one in the satellite, and it actually did obey the quantum mechanical property to where they, Schrödinger's cat, where it's both are zero, or if you measure this one, it's a 1, and that one in the satellite was 1, even though they're separated by lots of distance.
So that is something that we will cover later, quantum entanglement. But it is the base. If I said RSA encryption will easily be broken by quantum computing, the new encryption methodologies or algorithms will partially be based on quantum entanglement, and at least Chinese already demonstrated that this really works. And the core idea is that you can have. You start, for example, with one particle. You make two particles that are somehow entangled. It's not that they have a bridge or so, but then you take one particle under your arm, you walk away, and if you look at that particle, then at the same moment you know what the other particle also is. So it's not that information is being sent because the information was already there, but it allows you to agree on random numbers between two parties. So the number is random until you look at it, and that is what is key to encryption. So and one of the important consequences is if someone wants to sniff the network, he has to look at the key, and by looking at the key, you destroy the physical, you destroy the superposition state. So then the real recipient of the message can see, oh, this message has been tampered with. It's not the original one anymore. And that is what quantum cryptography is leveraging. That is based on the principle of entanglement, which we will briefly explain later.
Good. So what Johan was referring to is this idea of QKD, quantum key distribution. So you can over a quantum channel, then you can communicate a key. And then in the short term anyway, you might want to go ahead and use that key in classical cryptography, but you've been able to communicate the key knowing that it was not sniffed. So then the second paper is they did the same experiment, only did it satellite to ground. They shot a photon from the satellite to the ground that was entangled. So now the next thing we'll talk about is...
Time for questions.
Yeah, yeah. Oh, yeah. Any questions, anyone? Yes, your question. And shout it out, and I will repeat it.
You said RSAs become unuseful because of quantum technology. You also said there are problems that can be solved with quantum technology. Is there a cryptographic thing that can be solved with quantum?
Okay, so the question is, you mentioned that we did say that RSA at some point could become useless because quantum then can break the keys, and then is there a replacement, a quantum corollary?
There are problems that can be solved with quantum.
Yes. So yes, that is true. That at some point it'll break RSA, but then also you can leverage quantum computing then to teleport information and also to teleport keys and things like that. So there is a quantum cryptography that is available.
So actually, the quantum key distribution is a solution to this problem, because you don't know the key. The problem with one of the future issues with the RSA encryption is that you know the public key. It's not a secret. But if the key is not known until you look at it, then nobody can know the key, because once you know the key, then you know that the key has been tampered with. Because if because there are ways to find out if the key has been inspected already. And once the key is inspected, you're not safe anymore. But as long as the key is not inspected, you can't factorize it. So that is so here another quantum mechanical effect called entanglement is used to make up for the fact that we lose the safety, the security, because the integer factorization will be broken by quantum computers. But the new way of doing is, at least that's the way that people think now about it, that the new way for doing encryption will be based on quantum entanglement. And it is looking very, very promising, and there have been successful experiments about it. But I don't exclude that there will be another theory coming up with more success. It's not really the theory that matters. It's also how hard will it be to implement in hardware, because we are talking about, and I prefer talking about equations, and also mathematically we can do this and this and this and this, but still you need to do this in a computer, and that is for me the mind-boggling part, mind-blending part.
Yeah, mind-boggling.
Yeah, the difficult part. So that how can you get sort of a mini LHC and laser systems and measurement systems in such a small thing as a cell phone? That's extremely hard, and I really admire people working on the physical hardware. That's amazing. So and therefore evolutions there will in the end tell whether quantum entanglement will be suitable for encryption or not.
Okay, I'm going to go ahead and
sure.
go to representing. So now let's get into some,
So there were no more questions?
Any other questions? Yes, question. Okay, so the question is how long before RSA becomes useless? I don't know. I really don't know.
People are, it was some people that I very much respect, both independently from each other, told me 10 years. I think it will be sooner. The problem is, as I said, if you have a quantum computer with 100 qubits, will you tell anyone? So we don't know how fast it will go. And also, there will be a difference between the first quantum prototype that can factor those 4K bit numbers, but then it's not ready yet for production. So it's the time between the first prototype and something that can be used commercially or at least privately. There will still be some time, but I think it's definitely not going to happen this year, but it won't take 20 years.
So you don't know either, is what you're saying. Any other questions?
I said it in a more scientific way, I think.
Okay. Any other questions that neither one of us can answer? Okay. All right. So now we'll get into some practical things as far as things that we can relate to as developers. So starting from the very beginning, as developers, we all know about classical bits, on and off. With quantum computing, you have what's called a qubit. And as I mentioned, it can be either on, which is at the south pole there, that one, or off, which is at the north pole of the Bloch sphere, or it can be in any other state. And those states can be represented by any point on that Bloch sphere, on the surface of that Bloch sphere. And so, there's 3 degrees of freedom there, as far, like 3 axes that you can then use to point to any part. So, for example, what it's pointing to now is this superposition that's over on the right. This superposition, this combination, in algebra you could think of a linear combination of on and off. And because it's a circle, you're talking about a kind of a unit circle, a unit sphere, then the way to get to that point is 0 plus 1 divided by the root of 2. And so that would be an equal superposition of 0 and 1. I prefer, and a lot of people prefer to think of it not as you hear nowadays, 0 or 1 or both, at the same time. I prefer to think of it as more of a combination of both. And what it's really in is this state that isn't decided until it's measured. Right?
Yeah. So it's not about, and there's often a confusion. It's not about probabilities. It's not that there's a 60% chance that this qubit is 1. No, that qubit is 1 and 0 at the same moment. There are different representations. Different people have different opinions about how to visualize the state of a qubit. We will show a number of different ways. But the important thing, I think the important thing is that a qubit can be 0 and 1, or is in the superposition is 0 and 1 at the same time. And one of the consequences is if you have 2 bits, you can have 0, 0, 0, 1, 1, 0, or 1, 1. So you have 4 possibilities. But only if you have 2 bits, only one of those 4 possibilities is true at a given moment. And in quantum computing, they are those 4 possibilities are valid at the same moment. And that offers lots of possibilities. Instead of doing 4 calculations with each composition of those bits, you can do 1 calculation. That's also mind-boggling thing.
It really is.
We will talk about it later.
So what this represents, if you're looking at the slides or even later, there's a link down here to a really cool site called Desmos that's nice for being able to visualize different mathematical things, like in this case trigonometry. And I created an image that then represents the points, some of the points on a unit circle that represent the state of a qubit. So now, unlike the block sphere, which we saw just a second ago, so that was a spherical representation of a qubit. Okay, we have a sphere there. Unlike that block sphere, there's another way, as Johan mentioned. You can represent it with just a flat unit circle, and so in that unit circle, you can think of it as a plane, right? Where you have and kind of like a plane and an associated vector, right? Where you have these orthogonal bases, where you have 0 here and 1 here, and then so the state of the qubit could either be 0, or it could be 1, or it could be in that superposition, which you can represent as this plus. And that superposition, you might remember from the block sphere slide, is some combination. So the combination you can represent is 1 over root 2, 0, and 1 over root 2, 1, and that's this position on the sphere, on the circle, which happens to be here, the square root of 1 over the square root of 2 on the x-axis, and then 1 over the square root of 2 on the y-axis, which then is this point on that circle. By the same token, you could have minus something that's minus on the 0 axis and plus on the 1 axis, or even minus on both axes. Now the thing about qubits is that, and if you look over on the left here, the thing about qubits is that you have the states of 0 and 1 are expressed in some number. It can be real numbers like you see here. It can also be complex numbers. But those numbers have an amplitude. In this case, if we, maybe I'll rotate it a little bit here and I'll pick on our equal superposition. That amplitude is 0.707, 1 over square root 2. And then if you take the square of an amplitude, that's the probability that it's going to be that in that state when it's measured. So in this...
Yeah, maybe one remark about it, that's important, how Jim said it, so that's a compliment. So it is the probability that it will have this state when it is measured. So it is, and that's very important, it is not the probability that it is at that moment in that state. So it keeps in the superposition state until it is measured. And that is the key thing about quantum computing, that it is both states together, and only when it is measured it will have that probability.
Yes, thank you. Well said. And that's a compliment too. So
that's all for the compliments for today.
Yeah, no more compliments.
Yeah.
Okay, so then in this state, for example, we have 0.887 for the 0 axis, and then 0.4817 on the 1 axis. And so then the probabilities up here, if you square them, then are, make this bigger so you can see it. The probabilities would be 0.21 probability that it'll be 0 when measured, and 0.78 probability that it'll be 1 when measured. And so the next slide will maybe shed some light on that. So these graphics are from a really good series. It's a 3-video series from PBS Infinite series on the math of quantum computers. And so I would recommend watching that series. It's three very short videos. But so you can represent qubits with a unit circle, and this is just what we were talking about a second ago. Here we just happen to have an amplitude on the x-axis of square root of 1/3, and an amplitude on the y-axis of square root of 2/3. So it's the probability then of when it's measured of being 0 would be the square root of 1/3 squared, which is 1/3. So it's a 1/3 probability that this would be measured as a 0 when it's measured, and a 2/3 probability that it'll be measured when it's 1. Another way of representing it is with vectors. I mean, these are, this is two-dimensional space here. You can have two-dimensional vectors. Well, you can represent it this way. So this would be the 0 state, because it's 1 in the 0 state, 0 in the 1 computational basis state, what they call that. So that would be the same as 0. And then here we've got 0, 1, which would be the 1 state. Or you could have linear combinations of those. So this 1/3 and 2/3, that's represented here. So we have the root of 1/3, 0, and the root of 2/3, 1, which would be a vector. A vector is just like a one-dimensional array kind of thing. And so you could represent it that way as well.
So the first two examples, the 0, and that's in the cat notation, the 0 and the 1, those are qubits that are not in a superposition. So the 0 is clearly in the state of 0. So that is not a superposition. It will always be 0. You know for sure that when it will be measured, it will be 0. The 1, when it will be measured, it will be 1. And so you can think of a qubit as a combination of how much 0 and how much 1. And the last example, the third one, that is a qubit in a superposition. And I think that's an important concept. If you see the 0 and 1 qubit is not in a superposition, but if it's both 0 and 1 at the same moment, then it is in a superposition, and then then you can do cool things with it, as we will show later. On classical bit, you apply classical gates. On quantum bit, you apply quantum gates, and therefore the way of how to represent a qubit is very important for doing mathematical calculations. So 1, 0 means it is 0, 0, 1 means it is 1, and anything in between means it is both.
So as far as like with classical computing, you represent ones and zeros in silicon, using transistors or whatever, right? But with quantum computing, we represent them in much different ways. And I'm going to ask the physicist how we represent those. Yeah,
well, the fact that we have a real one with a PhD in physics scares me a bit. I have to explain this. So correct me when I'm wrong. Representing qubits can be done in a number of ways. So there are different quantum computer prototypes that are using different technologies. But for example, a photon, and Jim has a very nice demonstration. Will the demo work?
Yeah.
Okay, cool. Has a very nice demonstration about it. The polarization of a photon can be horizontal, or vertical. Or it can be horizontal and vertical at the same moment. So that information about the polarization type of a photon can be used as a qubit. So that is a physical process that's from something that can be in two states at the same moment until you measure it. Then it is horizontal or vertical. So that matches that mathematical concept. Electrons can have a spin up or down, and you don't know until you measure. So it is an up and down at the same moment. So it can also represent a qubit, and it seems that this is being used a lot lately. if you use superconducting characteristics, then and you measure the charge, something can be charged or uncharged at the same moment until you measure it again. So these are three physical concepts that share this idea of being in two states at the same moment until you measure it. And I think in the end, one of those, there are a number of others as well, but I don't know which one will ultimately win. I think, and I was, we actually prepared this presentation, so I was reading about quantum computing earlier today. And I read about photons, and that article said it's actually very easy to split a photon and create two entangled photons. I think, well, that's slightly exaggerated, but how easy it will be to create this on a scale will determine how quantum computers will really look like. At this moment, it seems to me that superconductors, which require low temperature, seem to be not impossible to create. So maybe that will be the basis for the future quantum computers. But it can also be photons or electrons, of course. Okay, Jim, you have to smile because the picture is taken. Meanwhile, I will answer a question if that's okay. Yes.
You say it can be two different states at the same time until you measure it.
Yes.
Okay, wait, repeat the question.
No, he's still asking the question. How can I repeat the
Well,
question?
you're
that's still
talking to
being
him,
asked?
and you're not, but nobody else can hear what he's saying.
No. I try to understand the question.
All right, go ahead.
How do you know it without measuring it?
Sorry, can you repeat the question?
You say it can be both states at the same time until you measure it.
Yes.
How do you know it without measuring it?
You don't.
Okay, so could you repeat the
So,
question? Nobody else can.
So the question was, the question was, I said that it can be in two states at the same moment until you measure it. So, and then how do you know it without measuring it? And the thing is, you don't know. But that is, actually, that is a very good question. We were giving this presentation at Java 1 a couple of weeks ago, and we got the same question. And I had an extremely hard time to answer it, and Jim was no useful at all. So I thought a lot about it, and we added a great slide. I think, at least, we added a great slide to explain this. But spoiler, you all know Java 8 probably here. Who isn't familiar with the parallel streams in Java 8? Okay. So with parallel streams, you can have a collection, a Java util collection, and you want to do some processing on it. With a parallel stream, you can, for example, if the processing is, I want to multiply all the numbers in this collection by 2. With serial processing, you first take the first and the second and the third and so. But with parallel processing, you can have all those numbers to be multiplied by 2 at the same moment. Okay, it is with different threads because we're still talking classical computing. And then, after this parallel step, you can then reduce the result or map it to the sum of all those numbers. So we have a collection, 1, 2, 3, 4. We want to multiply every element by 2 and then take the sum. So if, and the end result is only one number. So we don't care about all the intermediate results. As long as they are computed in the right way, we don't care. We are only interested in the measurement, which can be a very simple number. It can be even 0 or 1. And the same holds with the quantum computing. Does it mean that I'm talking too long?
No.
Okay, good.
You're
so
fine.
the same holds with doing these computations using a quantum computer. You don't care about the intermediate steps. You only care about the result. But that also explains why quantum computer is not suited for all problems, because it's not only that you don't care about those intermediate results, you can't care about them, because if you measure them, bang, your system is gone. So this is only applicable for systems where you don't care about the intermediate results, more or less. And there was another question there.
Different with Java optional because you can measure it twice.
Yeah, so the question was that it's different than Java.optional because there you can measure it twice. And that is very true. I'm not going to make a joke about it.
No, that's very good
because
point.
Brian Guts is not here. So
We'll just go ahead and move on here. So this is just an example of a chip. It's by Rigetti Computing in California, and so this they actually put at the bottom of a dilution refrigerator that's colder than outer space. And that way, on the chip that you see in the middle, I think they have 9 qubits on that they're working on that can then exhibit properties, quantum properties, and not be exposed to the outside world, because as soon as it's exposed, then it's instantly measured. As soon as it interacts with the outside world, it's measured, and then collapses, and so that's why it has to be so cold and isolated.
And that means that's actually coming back to that question. As soon as you measure it, it's the end of the story. So as long as you don't have to measure it, you can do strange things with it. But it is really true. And it sometimes reminds me. Do we have time for a joke anecdote?
How long is it?
Yeah, 30 seconds.
30 seconds, yeah.
Okay,
sure.
so for example, this is my cell phone, and this can be teleported. So I will put it in my pocket here, and now I say hocus pocus pats, and the cell phone is in Jim's pocket. Don't show it, because then we break the measurement. Now I will do a second teleportation, hocus pocus pats, and the cell phone is transported back into my pocket. See? It worked. So that is actually what we are trying to explain here. At least that's what they taught us. So with quantum computing, you have to believe everything that's happening in between, but you can't see it. You can only see the end result. And
that's a good one. I like that. So now we're going to talk about...
It wasn't too long?
No, it was
okay,
good.
Good, yeah.
The axiom of quantum mechanics. So there are 3. There's the superposition principle, which we've kind of talked about, where it can be in one state or another state, a 1 or a 0, or some combination. I'm going to keep saying, some combination of both. You tend to be of the religion of they can be both at the same time. I say it's a combination of both, or you don't know until you measure it.
I think that's okay. The only thing that I think is not okay if you say that it has a probability of so much.
Right. Okay. All right. Good. And so we have the superposition principle. Then we have this idea of measurement. And then we have this thing called unitary evolution. And what that is over time, qubits can change. The quantum state can change. And that's how you program a quantum computer, using these gates that provide this unitary evolution. The reason why they call it unitary is because you've got the unit circle. Each qubit can be represented on the unit circle. So the evolution, these gates that you have that change it from one state to another, retains that unit norm. And in addition, they're also reversible. It's kind of cool with quantum computing. You can take it through a gate, and then so you do a computation, and another computation, and then you can reverse that. It's completely reversible, so you can back it all the way up to the beginning state. So we're going to delve into that.
So slowly we are moving from the conceptual things of quantum computing into how you can program for quantum computing.
That's right, yeah. Very good.
Okay.
Yeah, thank you.
Yeah, make a note.
First we're going to show a science experiment. Martin Klein is going to help me. And what we're going to do is show you this idea of superposition states and then a measurement. And so we'll do the experiment first here, Martin. If I couldn't really, being a theoretical guy, I couldn't really, trust your ability to set up the experiment. So I had Martin do it. So what we've got here is 3 polarized filters. Remember, light can be polarized, or photons are polarized, and so this filter is polarized vertically. So when photons come through it, like you can see photons coming through it, right? So you can see photons coming through it, but when they go through it, because it's polarized, as they hit that, as a photon hits it, it collapses. They're photons that were already vertically polarized are going to come right through. Any ones that weren't vertically polarized are going to collapse into either vertical or horizontal, because we're measuring in that basis, in the vertical horizontal basis. So they're collapsing. Some of them are going to collapse horizontally, and so we're not going to see it. But some will collapse vertically, and those are the ones that we see. So now let's say one collapses vertically. Then if you put the other one in front of it so we can see all the light. Now, so they're both positioned, they're both oriented with vertical polarization. So it hits the first filter, it collapses in the vertical state. We'll call that 1. And then it goes to the next one. Well, it's already in the vertical state, and so it's not in a superposition relative to the second one. It's just going to pass right through because it's already vertical. So 100% of the light that gets through the first filter is going to get through the second filter. But if you'll rotate the second filter slowly, now we see that now we have a 90 degree. So going through the first filter, it collapsed to the horizontal state, quantum state. But now the second filter is horizontal, and as Johan mentioned, when you're in one state, and now it's in that state. So none of the photons that got through the first filter are going to get through the second filter, because it's not possible for them to collapse in the horizontal state, because they're not in a superposition. They're in that vertical state. But now the cool thing is that because of that, and I'll do the thought experiment first before you do this. If we interpose we see no light now, but if we interpose a filter that is polarized at 45 degrees, we would expect that because we've added another filter, that we will see, no light still. But what's surprising is that we will actually see 25% of the light that comes through the first filter. And so if you'll do that, then I'll explain why that happens. So now we can suddenly see 25% of the light that's coming through that first filter, even though we've added yet another layer. Okay, so now I'd like to kind of explain that, and I may need Johan's help to explain it. Thank you very much. You've been a great assistant. All right. Yes. Okay.
So why don't you ask Martin to explain it? If I wasn't allowed to do the experiment, then...
Yes, I don't know.
Go on. Explain it,
Okay.
I'm interested.
No, okay, so I'll talk, and then you can help me. Okay, so this is what we did. So we have over on the left, we see light coming in, and by the way, this comes from a really nice video from 3 Blue 1 Brown. They have some great videos on mostly on math stuff, and they did a quantum thing with minute physics. So I would really encourage you to go watch this video. But in a nutshell, what happens is you see the blue polarization there coming in on the left, and that's at that 45-degree angle, let's say, and then it hits this vertically polarized filter, and some of them are going to collapse in the vertical position. And so the blue coming in, you could think of it as in that equal superposition up there, the one that's marked with the diagonal line, and root of half horizontal, root of half vertical. So it's in that position, but then it collapses from that diagonal position to the vertical position. So that was that first filter, photons coming through the first filter. And then what happens is, here we're measuring it in the computational basis. We're measuring it with vertically and horizontally. Well, the horizontal we're saying is the 0 state. The vertical is the 1 state. And so maybe if this light here, if the light was the photons were polarized in this position, then it's going to collapse in either a 0 or a 1. The probability being more 0 than 1. And so then what happens is we saw this. We saw when we had 90-degree filters there that we saw no light come through. And then, so photons that make it here through this first filter aren't going to make it through that filter. And we saw that in our experiment because it's been decided that they are vertically polarized and it has collapsed vertically. And so it's not possible. It's not in a superposition anymore where it could collapse to 90 degrees. And then we interpose that lens at 45 degrees, and that actually lets more light through. And what happens there is it was 45 degrees off, that one in the middle. And so what happens is that middle filter measured the state, the photon, in an alternative basis. And so if the photon was coming in vertically oriented, and since we measured it in this other basis, then it's in a superposition relative to that basis. And so it could collapse then to either the plus basis or the minus basis, and that's why, and so 50% of the light can come through then that second filter. And then when you have another filter 50%, that third filter, another 50%, because it's the same story. It's been measured in the computational basis. And so now 50% of the light can get through that filter. So that's why we saw 25% of the light get through from end to end through those three filters. So questions on that, please? Questions? Yes, yes, your hand, yes.
Doesn't the fact that when measuring noise in the experiment pose a threat, as in it would not be accurate?
I'm sorry, could you repeat it but a little louder, please?
You said that the experiment would be ruined when you measure it to be done. Doesn't that make it inaccurate if you measure it at the wrong time?
Okay, so the question is I said, if it's the experiment is you're done when it's measured, right? That collapses it. So wouldn't that make this experiment inaccurate? And so when we expose the light, when we shoot a photon through a polarized filter, that measures it. So in that first photon, its new state, it collapsed to anything that got through collapsed to the vertical state. So that's its measured state. But now, the only ones that got through were ones that either were originally in the vertical state or collapsed to the vertical polarization. So now it's in some quantum state, ready to be measured again, right? So it's in a quantum state of a vertical. We know that now. And so now it's ready to be measured again with another filter. So it's actually three different measurements rather than this idea then of like deferring measurements and then only measuring it at the end. We're actually, in that experiment just now, we measured it 3 times in 3 different bases. Okay, other questions? Yes, you have a question?
At the beginning, the lens was loose, the polarized end was loose, and the light was not passing anymore. Is it because the camera already has another polarization?
Okay, so the question is, is when we did this. Okay, when we did this, so the light's polarized vertically, and then here it's able to get through. But then when Martin did this, it... Yeah. I think that there must be some polarization in the camera lens, or in the filter or something. Okay, so the projector has some polarization. Okay, that's a very good point. So yeah, that's even a fourth filter in the experiment. One more question before we move on. Yes.
Yeah, you said the photons can be horizontally or vertically polarized, and refer to this as the bits 0 or 1. But what does mean vertically or horizontally? It doesn't have to do with gravity, because here horizontally is different from somewhere else on the Earth. Does it only make sense when you start with one filter polarizing? When do you define what is horizontally and what is vertically?
Okay, so the question then has to do with what is vertical, what is horizontal. It's because of gravity, or where you are on the Earth. What's the frame of reference, and so I may need Johan's help on this, but photons can be can be polarized in 360 degrees any way, right? And so when we hold a vertically polarized filter up, the point is that they're either going to collapse, or if it wasn't originally polarized in the same direction as the filter, or it didn't collapse in that polarization, in that orientation. Or if it collapsed in that orientation, then it's going to get through. And so now that's your, regardless of whether you call it horizontal or vertical, or whether there's an angle or whatever, that is the state that it collapsed to. And then relative to that, when you take another measurement, like in that alternate basis, it's going to be relative to that you're measuring. And so there's not this ground truth of what is horizontal and vertical. It's just.
I think maybe the confusion comes from. I think I heard in the question whether it's horizontal or vertical, and it is not horizontal or vertical until you measure it. It is both, so it's not that some light waves are going like this and others are going like that. They can be horizontally and vertically in a combination together. And only when you measure it in a certain reference system, as James said, then you can talk about, so this is to my measurement system, this is horizontal and this is vertical. But it's not that, for example, that it's relative to the Earth or so. So there's no zero coordinate system for this. Yes, well, so
repeat a supposition, please.
So the question was, it's only an instrument to create a classical bit because you can't work with something in between. Well, you want to work with something in between as long as possible, and only measure it when you need to know whether it's 0 or 1. And then indeed, if you're at the end of your experiment and you need to measure it, then you use this filter for saying, is this now 1 or is this now 0 indeed.
And we'll show that in some of the examples. So there's this famous experiment called the double slit experiment, and it's been used for classical physics, but it's also something that demonstrates in a very real way the wave property of quantum mechanics. And so we're gonna expose you to it now if you haven't already been exposed to that, and then we're going to leverage it later in some quantum algorithms. So from a physical side,
we will explain it later. The thing that we wanted, we brought this up in front now because the idea of this is that you can have constructive and destructive interference. So the bright spots here are constructive, and the black spots are destructive interference. So, and we'll explain it later. But the basic idea, because now we're going to the algorithms, the basic idea is that in order to solve a quantum mechanical problem, we want to constructively interfere the things that contribute to the solution, and we want to destruct the other information. So a common thing in quantum algorithms is that you first shift the problem somehow. Because with the problem, how it is exposed in the beginning, you can't really do something. But by shifting, or by shifting some qubits and not others, by using operations on them, the problem area is slightly different. And by doing those shifting, you can have constructive interference on one hand, on the things that you want to expose, and destructive interference on the things that you don't care about.
Okay, so so that in the classic, or in the double slit experiment, just let me explain it just a second here. So you have photons coming in from the left, and those, because of the quantum nature of the wave nature of quantum mechanics, you have those photons interfere with each other, and so we see then that wave pattern, and as Johan mentioned, then on the screen, then we see that on the back wall there, that we have constructive and destructive interference, and so that just demonstrates that the light, the photons, obey quantum mechanical principles. And so we said that to then be able to set up for some algorithms. So when you talk about quantum algorithms, we mentioned this unitary, these gates that we're going to have, unitary evolution kind of gates. So with classical gates, you have AND gates, you have NOT gates, you have OR gates. We're all familiar with those. Those work on combinations of bits, but then with quantum algorithms, you have quantum gates, and so some of those are similar. Where we have, for example, we have a NOT gate. It's also called a poly X gate. There's the notation for it, but it'll take a qubit and it will do a NOT on it. So it flips the state. It'll flip a 0 qubit to a 1, or a 1 to a 0. And then if you're into linear algebra, here's the matrix that then performs that operation. So you remember a qubit can be represented in a vector, and so we can multiply that vector by, or the matrix by the vector, and then in this case, with this gate, it would flip the bit.
So they told me that every equation would decrease the audience by a half, so I wasn't allowed to write any equation in there. I assumed we would only have one person, and I didn't want to see that person split. But matrix computation is actually very easy, at least at the level of one gate on one qubit. But the other principles are exactly the same, but just on bigger matrices. But so the NOT gate, as James said, can be represented by this matrix. And if you think about, if you remember how a qubit in state 0 is represented, it's represented by the vector 1, 0, because it's 100% chance being in 0 and 0% chance being in 1. So that is 1, 0. If you multiply the matrix 0, 1, 1, 0 with 0, 1, so it's the first row times the first column, so that's 0, 1 is 0 plus 1 times 0 is 0, so that's 0 at the bottom. and 1 times 1 plus 0 times 0 is 1 at the bottom. So we will turn the 1 0 into a 0 1. So that means that the qubit 0 became a qubit 1. I didn't show an equation, I just explained the equation.
But half the audience is going to walk out anyway.
But I think that I think that
Actually, they're all going to walk out because it's time for a break.
yeah.
So let's get back together at 10 after 3, please. All right.
Oh yeah, maybe before they leave, we have what we will do after the break is we will continue with the quantum gates, and then we will show some very basic tools that can help you create quantum algorithms, so that you can play with the quantum gates on the qubits. Actually, I think that's the fun part.
Yeah, I think they want to go though for 20 minutes. Take a
Yep.
break.
Okay.
All right.
You can take a break.
All right. Bye. See you in a little bit. Back, everyone. Welcome back, everyone. So we're going to continue with some quantum gates, and so we went through the NOT gate, which flips bits, and then we have the Z gate, which is used sometimes. We have this Hadamard gate, and you'll see Hadamard a lot, and and then we have this controlled NOT gate. Now the ones above it work on 1 qubit. The C-NOT gate actually works on 2 qubits, and you'll see that in a minute. We also have some other quantum gates that have to do with changing phases, the S gate and the T gate. We won't really deal with those much in this presentation. Also, in order to physically realize these gates, these transformations of qubits and quantum states, there's an example of some quantum gate hardware. And if you could briefly discuss that, I'd appreciate that.
Yeah, well, yeah, it's not a real hardware, but so I'm by no means an expert in this hardware. It's must be extremely complex to realize this. But the C-NOT gate, actually we took a bad example of this, but the C-NOT, the controlled NOT gate, first have to explain it. It operates on 2 qubits, as Jim was telling, and so it doesn't touch the first qubit, but the value of the second qubit is will be applied with a NOT transformation if the first qubit was true, 1. So and if it's 0, nothing happens. So that is a controlled NOT. So the first qubit is only used as a probe. So depending on the value of the first qubit, the second qubit will be flipped or not. Then you need some hardware to not measure the first qubit, because if you measure that first qubit, it will be you can't use it anymore, because it will be to its ground state again. So you need to use that state, and you need to use the information of that state to either flip the second qubit or not. And that is more or less what's shown in here. The polarization of the incoming wave there, which is the representation of the second qubit, remains intact in case the first qubit, the control qubit, is 0. But in case that control qubit is 1, then the polarization of that photon will flip from vertical to horizontal. So I think you can imagine at least, well, already a classical computer with transistors, which are pretty simple compared to this, but still it's amazing how they can have so many transistors on such a small chip. Now imagine that you need a system like this on a small chip. That is really amazing, and that's why for me it's impossible to predict how long it will take before this becomes commercially available, because I've no idea how to do that. But clearly there are experiments that are doing this. So there are quantum computers that are doing this, that have these gates, and these gates are exactly what is needed in order to create the quantum computer. And the physical processes need to happen inside your computer, not in the CERN infrastructure. It needs to happen in your computer. So you need to have a wave, polarized wave, and flipped polarization, and so that's really amazing on how you can do that in such a small area.
Yeah, so that's one example, right, where the qubits would be represented as photons, like some of the hardware that we talked about. It's electrons, in superconducting states, and so the way to evolve a qubit from one state to another with electrons might be electronic pulses or something that disturbs it, which could be much smaller, right? Okay, so here's we're going to examine some of these gates and what they do in the unit circle. Remember, a qubit can be represented in a unit circle here with 0 this way, 0 this way. What happens with the poly X gate is that it has the effect of rotating in this diagonal direction so that the 1 becomes a 0, the 0 becomes a 1. So we've in effect rotated it, that bit flip. And there's the corresponding matrix. There's a great series of videos, by the way. Here's a link to one of those videos by one of the pioneers of quantum computing, Umesh Vazirani. They're very entertaining videos and very, very dense with good information. So this particular graphic was taken from that. And then we have a poly Z gate. It flips the phase, and so so it is rotated around this horizontal axis. So 1 becomes -1, minus becomes 1. So that is flipping the phase. And then the plus state becomes minus, minus state becomes plus. If it's 0, then it just stays the same.
Can I now
Sure.
I remember that I should have interrupted you 2 hours ago about something. Unfortunately, we can't travel back in time yet. The -1 here might if you remember how I did the calculation, so without writing the equation, so 0, 1 becomes 1, 0. But if the values in the vector can be negative as well, and that's perfectly fine. But if you had can you bring that up? That external, the slide that I didn't want you to show. That one.
Yes, that one.
Okay. So and if you go to the negative.
Yeah, just I'll make them both directions negative. Okay.
So the key point in the vector representing a qubit is that it should somehow be 1. And that is important. Those are not probabilities, that if you sum them up, they become 1. But you'd have to take the squares of the values of the elements in the vector and sum those squares, and they should become 1. As a consequence, and therefore, if you're at 45 degrees, it's easy. If you have 1 divided by square root 2 and 1 divided by square root 2. So if you square them, it's 1/2 plus 1/2, that's 1. But if you have negative values, if you square them, do you say that in English? You square them?
Square them.
Okay,
Yeah.
good. That's very nice. We don't say that in Dutch. But square is not a Dutch word, so.
Okay.
So if we square them, they become positive values. So therefore, it's perfectly legal to work with negative values, and those are not negative probabilities. So that's not mind-boggling. It's not that this qubit has a negative chance of being 1 or so. That's not the case. The values are easy for computations, but have nothing to do with probability of being measured. So therefore, the important thing is, and all the matrices, so maybe now we can go back to the other side. All those matrices or unitary matrices, that's not entirely true. They keep the total probabilities of measuring any state the same. So they are not altering the system in a way that it becomes physically impossible. So those gates that we have here need somehow be represented by a physical process, so they have to obey the physical laws. And therefore the -1 here is not contradictory to intuition, where, that means that we will have a negative probability. No, it's not.
Yes. because you're taking the square, which makes it positive. And this always, whether you're talking about 1 qubit or 2 qubits or however many qubits, the total probability when you add up all of the amplitudes and square them is always 1. So that's why it's unitary. So then we have this very useful gate that you'll see a lot. It's called the Hadamard gate. And what that does is that will rotate, it'll flip along this axis. And so a 1 is going to become a minus in the minus state. And a 0 will become in the plus state. And so here is the vector, or sorry, the matrix that is applied to the vector. And so here, this is the H stands for Hadamard gate. So if we took the 0 state and applied the Hadamard gate, it's just saying that it's going to be in the plus state. And that plus state, as we saw on an earlier slide, is a superposition, an equal superposition of 0 and 1. And then if you take a Hadamard gate and apply it to a 1, then it's going to be in the minus state, this one right here, which is in a superposition of 1 over the root of 2, 0, and then minus the 1 over root of 2, 1. And as Johan just mentioned, that's not a contradiction, because if you square a minus 1 over root 2, what you get is half. And then you square this 1 over root 2, you get half. So it will, if measured, it will still, the probability that this was going to be measured as a half, and the probability that it'll be measured this way is a half.
Yeah, there were actually 3 things I wanted to add here.
Okay.
Yeah, one of them I forgot already. The second one is what you just said. This matrix, why does it have why isn't it just 1, 1, 1 minus 1? Why is the square root of 2 there? Well, that is to keep the norm, so that if you apply them to a system, to a vector that sums up to 1, that it still says 1. And the third thing is that this Hadamard transform, you see that a lot in quantum computing. It transforms, it brings a qubit that is not in a superposition into a superposition with equal values for being 0 or being 1. So it is, yeah, you can consider that as a launch state for qubits. So you start with a clear 0, 1, but if you apply a NOT and a controlled NOT and whatever gates, then it stays in a 0 or a 1, and then you're more or less doing classical computing. But by applying a Hadamard transform, you bring the qubit in a superposition. And then you can start doing the cool things, because then it's both 0 and 1 at the same moment. Without doing this, it's either 0 or 1, and not everything in between. So Hadamard is extremely useful for launching it brings the qubit in a superposition, so it allows for doing all these computations in parallel.
Well said. Thank you.
And the fourth thing.
The fourth thing.
The fourth thing
You
was
said there
that
were 2 things.
3 things, but I forgot the first one, so
Okay.
I'm okay with adding a fourth thing, I think. The gates for this are, and that was actually what I was reading, because if you have a classical gate, you need some transistor technology to create it. If you have a Hadamard gate, we showed the hardware for a controlled NOT gate. For a Hadamard gate, you have similar hardware depending on what your physical representation of the qubit is. But for example, a photon can be, with some technologies, can be decayed into 2 other photons. But that really depends on what the underlying physical representation is. But there exists already hardware that allows you to bring a bit from 0 or 1 into this bit where it's in that superposition.
Good. Thank you. Thank you. Okay, so Johan talked about the C0 gate. So in quantum circuits, quantum programs, you can represent them as circuits. So each wire represents a qubit. So we have a qubit on the top coming in, the control qubit, and then we have a qubit on the bottom. And so if the one on the top is 1, then it'll flip the one on the bottom, but if it's 0, then it won't flip the one on the bottom. And so you get these states. So 0, 0 goes to 0, 0, 0, 1 goes to 0, 1, but 1, 0 goes to 1, 1, 1 because it's flipped that second bit. Also, here's how you would represent then these, and here's some formula for you. Wow. So you could represent 2 qubits as a superposition here, where you've got some value, some amplitude of 0, 0, some amplitude of 0, 1, amplitude of 1, 0, amplitude before a 1, 1. And then if you take a C0, then it's going to flip these bits, this one and this one, if the first one is a 1. And then here's the matrix. And so I'd like to, can we defer that and come back to it?
No, I
actually,
think it's nice to show this. No.
Okay. So, Johan, what are we looking at here? And we're going to flip this.
Yes. So what you were showing before was a formula, not an equation. You did it in an equal sign, so that's why people were not running away.
Okay, good.
This is maybe very theoretical so far, and a couple of days ago started working on how can we make this more visual. And there exist a number of tools already, but being Java developers, we wanted to do something in Java. So with a colleague at Gluon, we quickly wrote a Java-based quantum simulator, and I will show it how that goes. So this is just some work, a few days, well, actually a few hours probably, but it's something that you can use to simulate quantum algorithms, and that will hopefully make it more visual. We are making this open source, which means that we hope that many people will contribute to it. So on the left side, we represent qubits. Those qubits are all in the state 0, which means that they are off. And now we can apply gates. So for example, here I have a NOT gate, and the NOT gate changes the qubit from 0, from off to on. I can apply the NOT gate to other qubits as well. And the second gate that we want to show here and that we discussed is a Hadamard gate. And a Hadamard gate, if I apply it to the first qubit, will at the end of the line we see the measurements. So at this point we will measure the qubits. And if we measure those qubits now, there's a 50% chance that it will be in on and a 50% chance that it will be in off. And by applying gates to those lines, you construct algorithms. And if you want to add more qubits, you can add them, and you can apply more gates. And note that a Hadamard and a Hadamard will correct themselves. So superposition, and then another Hadamard will bring the original state back. So that is just a very simple simulator with only 2 gates. We plan to add more gates, and because we're doing this in Java, it's open source. So make sure. What I want to make sure is that you understand that this is a quantum simulator. So this is not a quantum computer in Java. So the code which we will make public if we clean it up a bit is just a Java code where we have a simulator interface, where we have a model which consists of gates and circuits. The simulator interface is implemented in a class local simulator, which will do the calculations. And if you look at the calculations, the core of the calculation, it's actually this. This is just a matrix computation. So it's nothing more or less than applying matrix operations on vectors. So it's a bit complex if you have different qubits that need to be combined at the same moment, but the core of it is just matrix computations. So the limitation of this is if we have 1 qubit, we have a 2 by 2 matrix. If we have 2 qubits, it's a 4 by 4. With 3 qubits, it's 8 by 8. So that sums up very fast. So if you have lots of qubits, you won't be able to do this anymore on a local system. And therefore, we plan to have another implementation of simulator, which will be in the cloud. So that's then going to be a cloud simulator. So we're looking for cloud providers to host this, because this can be computation incentive. But it's actually the same principle as, and so I want to give some credits to the guys from AI Solutions. They're a NASA contractor, and they have a client technology for doing deep space trajectory exploration. And on the device, it can be a laptop or a mobile device, they do calculations for seeing what the best orbits are for sending satellites and so. And if it requires lots of computations, they offload that to the cloud for doing the computation. So we plan to do something similar. So with a JavaVex user interface showing the simulator, and if it's simple calculations with a limited number of gates, you will do it on your local system. And if it's heavy, if there are many qubits, you will need lots of memory, and that's then something that we can offload to the cloud.
Okay, thank you, Johan.
So now you can...
Very nice, and just a couple days, huh? That was good stuff for just 2 days. And so what I'd like to do now is we've talked about 1 qubit and how that's represented, and now we'd like to go into how would multiple qubits be represented. Before I go into this other quantum simulator called Quark, I'd like to talk about representation of multiple qubits. I think you mentioned this was Ket notation, right? So when you see a line, a vertical line, and then this greater than sign and something inside of it.
You had it on your slide, but you didn't mention it, so I thought that I should mention it.
Yeah, no, I appreciate that.
Yeah.
So this is called Ket notation, and it was created by Paul Dirac, a physicist, and it's used a lot in physics, and its purpose is to be able to very succinctly, very easily represent vectors. And like an individual Ket, like this one, where we have just one zero in it, a zero in it, that would be, that's the state 0 that we talked about for a qubit. And so if I had state 0, 0, where I've got 2 qubits now in this combination of qubits, this composite state, then I could just put both zeros in the same Ket. And that is equivalent then to if I just had a 0 here and a 0 here, which is equivalent to multiplying, actually doing a tensor product of both of those qubits. Now recall that a 0 qubit is represented as a vector 1, 0. And then if we take the tensor multiplication, the tensor product of those two, then what we get is this vector. And
is everybody familiar with the tensor product of vectors?
Okay.
No, probably not. Unfortunately, I can't explain because I'm not allowed to put equations on slides.
Okay, so I'll walk through it. So if I want to take the tensor product of this and this, what you do is you multiply the second vector by each one of the first vector. So I would take this 1 and multiply it by 1, and that goes here. I take this 1 and multiply it by 0, that goes here. And the same thing, I take this 0, multiply it by 1, that goes here. 0, multiply it by 0, that goes here. So that's a tensor product, and this vector then represents the composite state of these 2 qubits. If I had 3 qubits, then I would have vector, as Johan mentioned, of 8 dimensions, 8 elements in it. If I had 10 qubits, a 10-qubit composite state, then I would have 1,024 elements, dimensions in my vector. There's a really good overview of that from a lecture notes from John Watrous of the University of Calgary that's worth diving into. What I'd like to do then is open up this quark...
Wait, can I maybe...
Sure. Yeah, go ahead.
Close the quark simulator? Oh, that's scary.
Close the quark.
Yeah.
Okay. All right. Sure.
Because
what's on your mind, man?
There are many, many ones and zeros here, and I can imagine it's quite confusing. Who is slightly confused?
Who is slightly confused is what he said.
Okay. Who is extremely confused? Okay. So maybe we need to spend a few seconds explaining...
Knock yourself out, man.
Explaining again what the 1, 0, 0, 0 mean. I mean, Jim did it by showing the equations, but this vector is a representation of the 2 qubits, and the one on top means that there's a 100% chance that if we measure the system, there's a 100% chance that the 2 qubits will be in the 0 state, 0, 0. There's 0% chance that the first qubit will be in the 0 state, and the second will be in the 1 state, 0 chance. There's also 0 chance that the first qubit will be in the 1 state, and the second will be in the 0 state. And there's also 0 chance that the first qubit will be in the 1 state, and the second will be in the 1 state as well. So this vector 1, 0, 0, 0 represents the
composite state?
The composite state, that's a nice word, composite state. We don't say that in Dutch either. You will see lots of, if you talk about quantum algorithms, you will see lots of those vectors. And applying gates on vectors is nothing more than multiplying matrices with those vectors. So that's why it's extremely important that you understand what those vectors mean. And it can be confusing, I understand, because the 1 here means it's about the combination of the 2 first qubits. So it is something that you need, and therefore I think it was nice that even though Jim tried to prevent me from showing a simple simulator, I think it's nice that you use a simple simulator for playing with very basic gates. And that's actually what Jim will do himself now.
Okay, thank you for that explanation. Okay, so
are people are people a little bit less confused now? Yeah, most are completely not confused anymore now. Jim?
Okay, that's good. So maybe visually will help as well. Okay, so you have a 2-qubit system here, both in the 0 state.
Oh, wait, I see most of the people. So they just saw the screen, and I think everything is clear now?
Okay, so we have a 2-qubit system. There's the top wire is the 0 qubit, another 0 qubit. If I wanted to express these together, it's the least significant qubit is at the top. So this is a 0, 0, just like we saw before. And so now if measured, there's a 0% chance that the 0 qubit would be measured as 1. And same thing with here. This is the block sphere representation of 0, which is, remember, pointing north. And then as Johan said, as he pointed out in that 4-dimensional vector, the composite state is 100% chance of being measured, that's that magnitude squared, 100% chance of being measured as 0, 0. See that amplitude of 0, 0 up there? And then amplitude of 0, 1 is the magnitude magnitude squared is 0. So there's a 0% chance that if this were measured, it would be 0, 1. A 0% chance of being measured at 1, 0. 0% chance of being measured as 1, 1. So these four the
vector that we showed on the previous slide is actually the same as what is here in these four elements. So, and therefore the 1 and the 0 help visualizing it. So the amplitude, the only one with an amplitude of 1 is the element in the 0, 0 position, which was at the top of the vector.
Yeah.
So it's all different ways for representing something pretty complex. And the Quark editor provides a number of ways to visualize it. And different people will prefer different visualizations. But I think that Quark simulator, if you... why don't you... weren't you going to show the NOT gate? Oh, yeah, that's
I'm
what you're
going
going
to
to
show
do.
0, 1
Okay,
now.
sorry, yeah, I was too fast. Go on.
No, that's okay. Did you have something to say, though? But
I was going to say this.
okay,
but
good.
No,
Yeah.
no, but it's better that you say it.
No, you
No,
can
I'm
say
thirsty,
it.
I
No,
want to drink.
please, you say it. After you. Okay, so...
It's time that you do something as well.
Yeah, okay, I guess I'll do my job here. Okay, so now here's another state, 0, 1. So that would be a ket 0 and a ket 1 there, or you could represent it as a two vectors, 1, 0, and then 0, 1. We tensor those up, and that would be this state, which is visually shown here. So 0, 1, 0, 0. So if we open that up in the quantum simulator here, let's see right there, and see I can drag a NOT gate here, down here. So now this represents 0, and that flipped this bit, this 0 qubit, into the 1 state. So now it's a 1. So the chance of being on, if that were measured, is 100%. And so then we see that the Bloch sphere is now pointing to the south pole, which is the 1 representation. And then here we see the amplitude of 0, 0 magnitude squared is 0. So 0% chance of, if this composite state were being measured, 0% chance of being 0, 0, but 100% chance of being 0, 1. So 0, 1, 0, 0, that maps to what we saw here, 0, 1, 0, 0. So it's just a visualization of what's happening in the matrix. And so then going on to maybe a little bit more complex, it's like a simple quantum circuit, but it's more complex than what we've talked about. It also leverages what the Hadamards and the superpositions that Johan just now talked about, where you could create a random number generator very easily with a quantum computer or a quantum simulator. So we have 3 qubits coming in, all in state 0. And then we apply this Hadamard transform, this Hadamard gate to each one of them. And what happens is that they go into, the Hadamard will transform it into, remember, a superposition, an equal superposition. So a 0, as you can see there on the on this drop down here, as a matrix, it transforms 0 into a square root of half 0, square root of half 1. And so it's an equal chance of being measured 0 or 1, which is what is reflected here. Each one of these qubits has an equal chance of being measured as 0 as it does 1. And that's also reflected here. In this quantum simulator, it samples the qubits as if measuring them. And so what we see here is the sampled state. So here it's sampling at 0, 1, 0, 0, 0, 1, 0, 0, 0. So it's, and then we see the decimal representation as well. And we also see the chance of each one of them being, each state is being measured. So what we've done here is basically create a random number generator that because of the underlying, if this were a real quantum computer, because of the underlying quantum mechanics, just naturally generates, collapses into random states if you've got equal superposition. So then the composite state is represented over here. So the chance of the random number being 0, 0, 0, like qubit 0, 0, 0, is 12.5%, which is 1/8. Same thing with 0, 0, 1, etc. And so this is the composite state.
And note that this is now the first time that this composite state does not consist of zeros and one only. So the amplitude, the value is, if you remember from the previous one, we were simply playing with not gates, then we had all zeros and one state was 1, because then we weren't in a superposition. But now this is the first time that the amplitude is not 1. But if you, can you move over? So the value is, of that amplitude is 0.35. If you square that, you will get about 0.125. You will actually get exactly that. And because all values are equal, all the 8 values are equal here, 8 times 12.5% is 100%. So that's the check that in the end always needs to hold. The previous examples were very simple. All zeros and 1 and 1. So if you square 1 and count it to all the zeros, you have 1 here. But now here, there's not a single truth. There's just possibilities that if you measure it, it will be one of those states. So here we have for the first time an amplitude that's not 0 or 1. Is that more or less clear?
Okay, any questions at this point?
Yeah, we forgot to ask about questions.
Yeah, questions. Any questions?
I got an interesting question at the break, but...
was it about this?
Was
it on topic here?
It was definitely on topic. I'll think about it and I will come back to it later.
All right, you'll forget. You'll forget that you were going to think about it. Okay, so here's a Dilbert cartoon on quantum superpositions and observability. So we're going to be talking more about measurement now. So I'll just let you read it. Okay, so now measuring qubits. For example, when we start out, let's say we have this composite state of 0, 0, and then we run it through some quantum gate, and maybe that quantum gate results in the new state, the new quantum state, being square root of half in one position, in 0, 1, and square root of half of 1, 0. And so notice that 0, 0 isn't represented and 1, 1 isn't represented. The total composite state of the quantum state there is just half probability that it would collapse if measured to 0, 1, and then half probability to 1, 0. And then we have another quantum gate that let's say that it evolves it transforms it to this state where it's the root of half of being measured 0, 1, the root of 1/6 being measured 1, 0, and the root of 1/3 being measured 1, 1. And then we observe it. So it's got, it will, with probability half, it will be observed as 0, 1, probability 1/6 as 1, 0, probability of 1, 1, of 1/3 being measured as 1, 1. And so there's this whole, the irony, I guess, of quantum computing is that when you're creating, like you've got qubits, right? And you're creating through gates, you're evolving these qubits, and you might have, let's say that Google successfully makes a 49 qubit machine here in the next 2 or 3 years. Well, what's 2 to the 49th power? It's a really big number, right? And so you have that many states, millions of states, and each one of those states then has associated with it some complex number that's an amplitude. And so pretty soon, you have this if you had 100 or 200 qubits, I don't know what the maximum is, but it would take as many particles as there are in the visible universe to be able to hold all that, right? But that's the idea, is that nature, you're hacking nature's computer, hence the talk. And so you're setting up these quantum states that are being physically kind of held by nature in the universe, right? And you're able to then take quantum gates and evolve that state and do these calculations like factoring large prime numbers and doing all this magical stuff. But the irony is that when you measure it, when you try to get some useful answer out of it, it collapses into one state. Okay, it is 0001, or it is whatever. And so nature has opened herself up to these great computations, but then when you try to, you can't look at what the intermediate states are. All you can see is, an answer like, the probability of the prime factor being this of that number is, there's a 75% chance that the prime factor is one of the prime factors is 19, that type of thing. And so that's what, that's the, oh, did you fall asleep while I was saying that?
I was actually thinking on how to explain this slide, and right when you switched to it, I got it.
Okay, good. Well, that's good.
Thank you.
Right, so I thought you were nodding off, falling asleep.
No, I was thinking that during the break
Okay.
I didn't get a cookie.
Well, get this man a cookie. Somebody get this man a cookie. Right?
I was thinking about sending a message to Stefan for reserving a cookie for me.
All right.
No, so this is actually what I explained in the beginning without this slide. So the parallel with parallel processing in Java. I like that. The audience likes it too.
So since you've already explained it, do you need to explain it again?
Yes, because I have hopefully an idea on how you can value why quantum computing is so powerful, even though in the end you will only measure simple states. So as I said, in Java stream computations, you can use a parallel stream and then have each element of that stream being processed in parallel. Java will use a new thread for this, or a thread pool, so it doesn't really happen in parallel. But in quantum computing, it happens in parallel. In the end, you still have all the information in the same number of qubits as that you started with. But one example of an algorithm that doesn't exist and that you can probably also easily prove that it can't exist in quantum computing, but something similar does exist, and we will come back to that later, is suppose that I have 10 qubits, and I want, that means I can represent numbers from 0 to 1023, and I want to find the biggest prime number between 0 and 1023. What you would do in a classical computer is you start with 0. Is it a prime number? No, actually, yeah, you will start, of course, with the highest number and see, is it a prime? No, okay, then I will go one lower. Is it a prime? And I will go one lower, and so on and so on. But with quantum computing, it would be possible that you compute them all at once in one step, and the end result has the qubits in such a state that if you sum them up as bits, that has the highest prime number that can be represented with 10 bits. So I think so. Hopefully you understand now that even though in the end your information, all the intermediate information, is unavailable, you can't read what is happening in between, that the fact that you can have a result can be of enough information for solving a very complex problem. And that brings us actually to how, so that's the way how I like to explain it. Very complex problems can have very simple solutions. Do you hear me coming? The next slide?
Yes.
And very complex problems can require lots of computational power, and the result can still be very meaningful. For example, that's how Jim wants to explain it.
So, right, so Hitchhiker's Guide to the Galaxy, who knows deep thought? Okay, so deep thought took 7.5 million years of calculation to get the life to, or to get the answer to life, the universe, and everything, and came up with 42. And so, you know, here it comes up with the quantum state 42. So after all of that calculation and using all of the resources of the universe, then it measures one quantum state with some probability. And so that's the kind of analogy that I like to think of. So now we're going to go to quantum...
Questions?
Oh, questions. Yes, any questions?
There.
Is the thing that comes out of these quantum gates exact, or is it a chance that it will be correct?
Okay, so the question is the thing that comes out of these quantum gates exact, or is there, okay, so, or is there a chance that it will be incorrect? Okay.
Do you think that it will be the biggest prime number, or do you think that there is a 70% chance that it will be the...
Yeah.
Okay, so do we know that it will be the prime number, or is like there's 70% chance that it will be the prime number? And so the short answer is it's always a probability. Like when it collapses and it collapses to some state, then there's always a probability associated with it, right? There's a probability that it will collapse to this state. But when it collapses to that state, you don't know what the probability was that it was going to collapse to that state, but all you know is it collapsed to that particular state. Now, due to the nature of the algorithm, the way that you set things up, you may know that there's a 100% chance that it'll collapse to this state or that state, and so when you measure it, you know that that's the answer. But there may be another algorithm to where, for a different problem, to where the probabilities, maybe it's an 85% chance that it'll collapse to a particular state, and so you might have to measure it 3 or 4 times, you know, until you have the confidence that you get, you know, maybe 3 times that same answer, so you have a confidence that that's the correct answer.
So adding to that, so indeed, if your algorithm predicts that in the end you will have the exact 100% probability, then you're not yet fine, because in today's quantum processes there's still some error. So typically experiments are done a number of times to reduce the error. But that's one of the big things that they're working on in quantum computers, to reduce the error rate of the different gates. So that is still the case. But even then, if you need to do the algorithm 1,000 times or so, it's going to be much faster than infinite. And infinite is the time it would take to do it with a classical computer.
True. And to add to that, then, also, for every qubit that you have in a quantum computer, depending upon the underlying physical technology, you might need 100 or 1,000 qubits or whatever as error correction, right? So that's why the problem's so nasty as far as building a quantum computer. So now I think that we've said enough to where we can start into quantum algorithms. So that's where we're at, is quantum computing algorithms. And we're going to start with what I understand to be the very first quantum computing algorithm. And that's called Deutsch's algorithm. It was discovered or proposed in 1985, literally the hello world of quantum algorithms. And it's got 2 qubits. And I'll just go ahead and walk through this. This is a quantum computing circuit. We've got 2 wires coming in, 2 qubits coming in. We've got one in the 0 state coming in at the top. We've got one in the 1 state coming in at the bottom. So the state of the system at this point in time right here is 1, 0, because this is the least significant qubit. So now we send them through Hadamard gates. And so now the state of the system is going to be in an equal superposition of 4 different states, as we've talked about. And then we've got, and I'm going to walk through this again in more detail, but just overviewing. This is called an oracle, or a black box, that is going to handle some function. So it's a black box in the sense that you give it some argument in, and then it's going to give you some result out, but you don't know the internal workings of it. And then we're going to throw the bottom bit in the trash, and then we're going to apply a Hadamard on the top bit, the qubit. If I say bit, I mean qubit. And then we're going to measure it. And so that's the algorithm, and I'll delve more into that. So the algorithm is supposed to solve Deutsch's problem. So what is Deutsch's problem? So Deutsch's problem is, if you have a function that takes in 1 bit, and this time I do mean bit, I shouldn't have said that. It takes a 0 or a 1. And so if that function then, no matter what you pass in, returns the same thing, then we'll call that a constant function. So I pass a 0 in, it returns a 0. Pass in a 1, returns a 0. That's a constant function. Same thing as if it always returned a 1. That would be a constant function. But if it returns something consistent, but in a balanced way, we'll call that a balanced function. So if I pass in a 0 and it returns a 0, but if I pass in a 1, it returns a 1, every time, then we call that balanced. Conversely, we would also call it balanced if we send in a 0 and it returned a 1, or send in a 1 and it returned a 0. We'd call that balanced.
So the output is balanced. The output is constant, or the output is balanced.
Yes, thank you. And so then here is the black box, the oracle, then that will implement that function, and it's implemented as a quantum gate. Now, we've talked about how quantum gates are called unitary. They preserve the unit norm, which means that they, when you send something through a quantum gate, the probability of the system is always still going to be 1. It preserves the unit norm. But also, they're reversible. So as opposed to like an AND gate where you can have 2 inputs and 1 output, with quantum gates, you always have the same number of inputs as you do the outputs, because then they're reversible. You haven't lost any information. With an AND gate, if you have a 1 and a 0 going in, and the answer is 0 coming out, if you just had that 0, you can't reverse it. You don't know what came in. You've forgotten. But with a quantum gate, you have the same number of outputs as you do the inputs, and so you can reverse it. All quantum gates are reversible. You can reverse them. So the way that this quantum gate works is that the input comes in as a qubit. Let's say it's then a 0 or a 1 qubit. And then the output, for the output, the function is applied. So, if this were a constant function, that first one, when I said 0, if a 0 came in, then the function would be applied, and then this would be a 0. And then this stands for XOR, exclusive OR. We would exclusive OR it with whatever came in on the B. So if a 0 came in on the B, and then this function returned a B, or a 0, 0 exclusive OR 0 is exclusive OR is 0, because they're not exclusively OR. And so that's the idea here. So Deutsch's algorithm. So the question then is, how many queries of the oracle do we need to solve this problem, Deutsch's problem?
Maybe the problem that we want to solve is finding out if the function that we're investigating is that a balanced function or a constant function.
Sorry,
that is the problem.
That, yes.
It's always nice that you tell the solution, but it always helps if you first tell the problem.
Define the
as
problem,
well.
right?
Problem.
Yeah.
But in this case, and that's why I didn't want to make fun of you. But in this case, the problem is a bit weird, because the problem is that we not want to find the result of the function. We just want to know is this function balanced or not.
Mm-hmm.
It's extremely unuseful. It seems very unuseful, but that's why it's called the hello world of quantum computing, because it shows how you can compose gates to fix a problem, and it's the basis for the much more complex problems. So the problem is, do we have a balanced function or a constant function? We don't care which balanced function, which constant function. It's just, is it a balanced function or a constant function?
Thank you for doing that. Yeah, that makes it much clearer. Thank you.
Yeah. So the solution is more complex, but you will explain that.
Yes. So how many queries of the oracle would it take to solve? Well, classically, it would take 2. And so what I would do is, if I were trying to solve this, is I would pass in a 0 and then notice which one of these I got. Maybe I get a 1. And then I would pass in a 1, and I would note which one I got. Let's say I got a 1 again. And I would know, yeah, that's constant. But it's going to take 2 queries minimum, classically. So how many queries of the oracle to solve quantumly? And so now we're really getting to the heart of quantum algorithms and why they're useful. So quantumly, believe it or not, it takes 1. And the way that we do that is we create a superposition of inputs. We're going to do that with those Hadamards. And then we're going to leverage constructive and destructive interference, like we did with the double slit experiment, to then weed out the wrong answer and make the right answer appear. So how do we do that? So how would we do it classically? So remember, we use vector and matrix multiplication. By the way, when you're multiplying a vector by a matrix, do you just call that matrix multiplication, or do you always say vector and matrix multiplication? What do you call that?
Well, in Dutch we don't even use the word multiplication.
Okay.
So
All right. So thank you. Anyway,
that's very useful.
Yeah, that's really useful. So anyway, so this is a matrix, and it's called a permutation matrix. But anyway, it's the gate. It's the matrix that's going to that this oracle is going to use to take this input and produce this output. And so if I were going to, let's say that I wanted to pass a 0 into this function, and I get a 0, and then I pass a 1 in, and I get a 1. That's a balanced function. And so how is that implemented? Well, the matrix to implement that is right here. And so here's an example. I pass a 1 into this one. This is the least significant qubit right here. So I pass a 1 in, and if it's a balanced function, I'm going to expect to get a 1 out. So here's the transformation with a vector to matrix multiplication here. It's the second element here is a 1, and so what that does is that picks out the second column of this matrix, and so we can very easily see then that the result is this, which represents 1, 1. And so querying the oracle classically using the gate is just like this, and you would need to do that twice classically. So now with quantum parallelism, right? How would you do it quantumly? And so the kind of the common misperception as far as like quantum algorithms, how does a quantum computer work? The common misconception is that it tries all the answers in parallel. And it doesn't do that. But what it does is it sets up a superposition, kind of like the double slit experiment, and choreographs things to where it constructively makes the right answer appear, makes it more likely by having constructive interference, and then tries to weed out the wrong answers by having destructive interference. So the right answers would be brighter, and the wrong answers would be darker.
So here's the opportunity for you as developers, I think. When I said twice the analogy with the Java parallel streams, I tried to warn you that it's not as simple as that. So it's not that the quantum computing is doing everything there in parallel. You need to shift the problem a bit so that it can be solved much easier. And this very simple Hello World program is already difficult to understand. And the further we go with algorithms, for search algorithms, they become even more complex. And so there's definitely need for, well, first of all, the hardware need to be fixed. But that the hardware guys will do that. The second is that the algorithms need to be created in order to make quantum computing useful. And I think that on top of this low-level stuff that we are doing now, that you can build higher-level gates that you can then use for another way of programming in quantum computing without having to think too much about the low-level things that we are explaining now. So there's definitely a huge opportunity for developing quantum computings and developing quantum frameworks.
Absolutely. This is so Scott Aronson is one of the kind of luminaries in quantum computing, and I think he's a theoretical physicist at University of Texas, I think. But anyway, he has this he had this cartoon commissioned, which is kind of like the talk, the birds and the bees talk that you would have with your teenager, only it's the quantum computing talk. And so here's a link to the cartoon, but one of the frames in the cartoon is saying in quantum computing, the whole idea is just to choreograph a pattern of interference where the paths leading to each wrong answer interfere destructively and cancel out, while the paths leading to the right answer reinforce each other. And so that's what we're going to do in this one. And so this is a very busy slide, so we're not going to go through all the numbers, but I want to show you kind of how the constructive and destructive interference happens in these gates. So here, this is the Deutsch algorithm represented in gates, or it's kind of a little bit of a variation of Deutsch's algorithm represented here in this circuit. So you have the 0 coming in and a 1 coming in at the bottom, and then you run them through Hadamard's. And so this 0 and 1, actually, 1, 0, because this is the least significant, is represented by 0, 0, 1, 0. So this is 0, 0, 0, 1, 1, 0. So that's a 1, 0. And then we multiply it. We do a matrix to vector multiplication by this matrix. Well, what is this matrix? This matrix is 2 Hadamard gates, the tensor product of 2 Hadamard gates. Well, the Hadamard gate from a previous slide is this. So you would so if it were 1 qubit, you would take the state of 1 qubit, like a vector representing 1 qubit, and you would multiply it by this matrix. But if you have 2 Hadamards, on 2 adjacent wires here, then you take the tensor product, and so here we have the tensor product of.
Can I maybe?
Yes.
In general, and not allowed to write equations. If you have 2 qubits and you have 2 gates applying to the qubits, then the result is, so you have gate A to qubit X, gate B to qubit Y. The result is the tensor product of gate A and B times the tensor product of qubit X and qubit Y. That's something that you can prove, but that's also very important in all the algorithms here. So that means that you go from a 2 by 2 matrix for applying gates to 1 qubit to a 4 by 4 matrix to apply 2 gates to 2 different qubits. And that's the 4 by 4 matrix that you see there that's been applied.
Yeah, thank you. So now if we multiply this vector by this matrix, then that does, that's going to evolve the state to this next state. So if I multiply this by this, then now we have this superposition, which is represented here by this vector. And so notice that, half of them are plus, half of them are minus. Those are like the waves. These are, this state right here is like the wave pattern, the double slit experiment. And so now that's the input to our oracle, our black box.
Maybe just a question to the audience to see who's still awake. What is the chance, if we do a measurement right now, before we are at that oracle, what is the chance that we would measure the first qubit in a 1 state and the second qubit also in 1 state? Great.
Yeah, great. Yes,
Yeah.
25%. That's
if
right.
we had a book, we would hand it to you now.
Yes.
But it's square of a half, which is
right, the square of a half. Right. So now we're going to take it through this gate, this black box, which is represented with this permutation matrix. So notice that we're not going to query this oracle. We're not going to do this operation 2 times. We're just going to do it once. And so we so here's the state, here's the quantum state. And so we're just repeating that over here, the plus, plus, minus, minus. Going to multiply that by the matrix for the gate, and we end up with this superposition. So that's the superposition that we have at this point. And then we multiply it by the Hadamards. We send that superposition through these 2 Hadamards. So here's the superposition again repeated from down here. we multiply it by this matrix that represents the tensored up Hadamards, and we end up with 0, 0, 0, 1, which represents 1, 1. So this is kind of like a mini double slit experiment. So what we've done with this oracle here is we've orchestrated the constructive and destructive interference, and which ends up with this state, at this state. And then here we're focusing the light back onto the back wall, the back screen. This is the result of the constructive and destructive interference. And so that's the end of that state. So now, if you looked at four different situations here where you have, these are the
Four functions.
the four functions where you've got constant here, balanced here, and these are the circuits. Each one of these is an individual quirk circuit that represents that particular function algorithm. So here we have an oracle that does nothing. Here we have an oracle that flips the bottom bit, etc. And I'll get into one of those in a second. But what I want you to notice is the end result here. This slide answers the question, why could we do it in one query rather than needing two? Why did we only need one quantum query? And the reason is the superposition. We orchestrated this superposition to where when we measured it, it collapsed. If it was a constant function, the state is going to be here. It's going to be 1, 0 with 100% probability. And if it was this oracle here, the state, it's still going to be 1, 0 with 100% probability, but notice that the phase is reversed. And so, because of the constructive and destructive interference, we've set things up to where when it's measured, it's guaranteed that if it's a constant function, that the result will be the quantum state 1, 0. And then similarly, if it's balanced, there's a 100% probability where the state is going to be 1, 1. And so I can open up the quantum circuit, for example, for one of the constant functions and see, like, let's say this constant function. And we see, here's the state coming in, the Hadamard. This represents, as we saw, this is a representation of the vector, the plus, plus, minus, minus. And then we send it through this oracle. It's a very simple oracle here. We're just applying a NOT gate. And so then that flips the bit on the bottom wire. And then that is that minus, minus, plus, plus superposition that we saw. We send it through a Hadamard, measure it, and then it collapses to where 100% probability that the amplitude is 1, 0. And so we have just 7 minutes left.
So this shows that with one evaluation, we know whether the function is constant or balanced. We don't know which constant or which balanced, but for this problem, we didn't care. In classical computing, maybe we have to skip a few slides where you go to the numbers, because this problem can be repeated for higher numbers of higher qubits.
Okay. Okay, I'll go ahead and skip to. So now we're going to, thank you. We're going to go to the Deutsch-Józsa algorithm. Anybody Hungarian here? I need to know how to pronounce Józsa. Is that correct? Yeah, Józsa. Józsa? Okay, very good. Thank you. So it's the same problem, only it's kind of generalized. And here's the circuit, same circuit, but there's n number of qubits coming in to the function. So that's the Deutsch-Józsa algorithm, and it was proposed in 1992. And so it's still determine if the function is constant or balanced, but we have X number of bits coming in rather than just one. And so here we could have, let's say we set up the problem to where we have 3 qubits coming in from 0, 0, 0 to 1, 1, 1. And then if it was a constant function, it would always be either 0 or always be either 1. If it was balanced, then we could set it up, for example, if it's even, it'll be 0. If it's odd, it'll be 1. And then there's another function that if, it's just reversed.
To entanglement. But
okay.
maybe that's an important
okay.
thing.
And so classically, how many would it take? Well, it's going to take, for however many bits are coming in, it's going to take 2 to the n minus 1 of those bits plus 1. So if 8 bits coming in, you're going to have to query it 5 times. But with quantumly, it's exponentially faster. You just have to query it 1 time, and that is because if it's a constant function, there's a 100% probability that it will measure 0, 0, 0 because of this constructive interference. So here, it's perfectly constructive interference to where when you send it through Hadamard's, it's going to be 0, 0, 0, and 100% probability that it won't be 0, 0, 0 because of this destructive interference if it's a balanced function. So now I'm going to talk about quantum entanglement in the 4.5 minutes that we have left.
Well, no, we will use most of those time for Q&A,
okay,
and for showing the other algorithms. So
okay.
Quantum entanglement is very important, but because we have no time, I will just explain the very basic concept. With quantum computing, it is possible to create 2 qubits that are entangled, which means that they are related. They are in a superposition state, but if you measure one, and it turns out to be 1, then you know that the other one is 1 as well. And you can do that with qubits. So with 2 qubits, you entangle them, and then you move them to different locations, for example, a consumer and a producer. And that is what is used for encryption, for example, because the moment that the consumer reads his qubit, then the producer will have the same value. So that is actually distributing a random number between different users. The question in the break, and now I do remember it, was, yes, but if someone in the middle tries to read this qubit, then he destroys the information, but how does the sender, the receiver, knows that the information is being destroyed? Again, you do some of the operations like we did in the Deutsch algorithm. You don't directly measure that qubit that is entangled, but you add another qubit. You do some, for example, a C0 operation, and then based on the value of that qubit, you can of the control qubit, you can still see if the first is in a superposition or not. So, very briefly, entanglement combines allows you to share information, and the value of the qubit. Once you read it in qubit A, it's also it has the same value in qubit B, and that opens lots of possibilities for different algorithms. You have gates for it as well. We will skip the teleportation because I think what we wanted to do is very briefly show that we now show the hello world of algorithms, of quantum algorithms, but there are much more algorithms, and I think the Shor's algorithm.
Okay, good. Yeah. So there's a progression of algorithms, and you can go through these slides that kind of step by step takes you to where you can understand Shor's algorithm. And there's a really good video on Shor's algorithm.
We have 2 minutes. You can explain Shor's algorithm.
Right. So there are 4 steps to it. 3 of them are classical. Step 1,
I was joking.
3, and 4 are classical. The second one, finding the period of a number, then is one that quantum computers are really good at doing. There's something called quantum Fourier sampling that does a Fourier transform that makes it that it's very easy to do period finding the period of a function, which is something that is critical for being able to factor large numbers.
And which is much harder to do with classical computers. So that slide shows, I think, if you go back to the previous slide, showed actually what we said in the beginning. For some problem areas, quantum computing is best suited. For others, classical computer is best suited. And here it is shown that, and as we explained, that if you combine classical computing and quantum computing, you can easily break RSA encryption.
Yes, yes. So we have a minute and a half left. If you have questions, please let us know here. And then afterwards, then please come up and we'll be able to answer questions as well. But any questions now while we have some time? Okay. Questions? Do I see anybody?
There.
Okay. Yes, question. Okay, so the question is, what's the difference between a 0 and a 1? Because in both, when you send it through a Hadamard, because it goes through a superposition. So back on this, they're both in a superposition. So back on the gates, go back to the gates here. Yeah, here's Hadamard gate. So the 0, when you send it through a Hadamard gate, it goes to the plus state. And a 1, when you send it through a Hadamard, goes through the minus state. Well, the plus state is 1 over root 2, 0, and a 1 over root 2, 1. But the minus state is a 1 over root 2, 0, minus 1 over root 2, 1. And that in the Hello World algorithm, the Deutsch algorithm, was one of the keys to constructive and destructive interference. But what's interesting then is if you send it through a Hadamard, again, remember gates are reversible, and some gates are reversible by using the same gate. If I send it through the Hadamard again, it's going to end up as its original 1. So if I do 2 Hadamards on a 0, I would get a 0 back. 2 Hadamards on a 1, I would get a 1 back.
So the amplitude is the same, but the phase is different, and that's what you can keep in the follow-up gates. You can take that into account.
But if I measured it at this point, it's going to measure, with half probability of 1, half probability of 0. Thank you very much for your patience and your attentiveness. And if you have any more questions, please come up. Thank you.